Welcome to Talk Tensors.
Glad to be here for this one.
Yeah, I'm really excited about today's topic. On this deep dive, we are taking you, our fellow researchers, and, well, just curious minds back to a really pivotal moment in the history of machine learning.
A massive paradigm shift.
Exactly. A moment that fundamentally changed how we think about neural network architecture, data efficiency, and just the elegant manipulation of multidimensional spaces.
It really is a beautiful piece of engineering.
It is. Today, we are unpacking a seminal computer science paper from late 2017. It's titled StarGAN, Unified Generative Adversarial Networks for Multi-Domain Image-to-Image Translation. That was authored by UNGHOI and an incredible team of colleagues.
Right.
We're going to break down the exact problem they faced, the elegant topology they proposed to solve it, the underlying mathematical machinery, and ultimately, the lasting legacy this single paper left on the field of artificial intelligence.
It is a brilliant piece of work to revisit. I mean, to truly understand the impact of StarGAN, we really have to teleport ourselves back to the research environment of late 2017.
Set the stage for us.
So generative adversarial networks, or GANs, were experiencing this absolute renaissance. Ian Goodfellow had introduced the concept a few years prior, and by 2017, researchers were just obsessed with a specific application of GANs.
Image-to-image translation.
Exactly, image-to-image translation.
I remember that era vividly. The community was trying to figure out how to teach a machine to take an image in one format and seamlessly convert it into another.
Right, like turning a daylight photo into a nighttime scene.
Or translating a rough-line sketch of a handbag into a photorealistic image of a leather bag.
The prevailing state of the art at that exact moment for those specific tasks were models like Pix2Pix.
Yeah, Pix2Pix.
And while Pix2Pix was groundbreaking, it was incredibly hungry.
Hungry for data.
Yes, it required strictly paired data.
Let's clarify what strictly paired means in practice for you listening, because it was a massive logistical nightmare for researchers back then.
Oh, completely.
If you wanted to train Pix2Pix to turn sketches of shoes into photos of shoes, you could just download 1,000 random sketches and 1,000 random photos.
No, you needed a sketch of a shoe and a photograph of that exact specific shoe.
Right.
Not just the same model of shoe. The shoe had to be presented in the exact same orientation with the exact same lighting.
Occupying the exact same pixels on the canvas?
Exactly, because the network learned by calculating the pixel-by-pixel difference between its generated output and the ground truth target image.
So if your target photo was shifted even, like 5 pixels to the left compared to your sketch?
The pixel-wise math would just break down. The network would get completely confused and output this blurry, unusable mess.
And collecting that kind of perfectly aligned data is expensive, it's time-consuming, and for a lot of real-world problems, it's just physically impossible.
Right.
You can't get a perfectly aligned pair of photos of the exact same landscape in summer and winter without locking a camera on a tripod for 6 months.
Yeah, nobody has time for that. So the field was stuck, at least until researchers figured out how to break the paired data requirement.
Which was the next major leap.
Yes. Breakthrough models like CycleGAN, discoGAN, and UNIT emerged right around that time. They introduced mechanisms that allowed networks to learn from unpaired data.
That felt like absolute magic when it happened. I remember seeing the CycleGAN paper.
The horse and zebra one?
Yes. They took a pile of photographs of horses and a totally separate, completely unrelated pile of photographs of zebras.
Unaligned.
Completely unaligned. The horses were galloping in a field, the zebras were standing by a watering hole, zero alignment. And yet the network learned how to take a new photo of a horse and paint zebra stripes onto it, perfectly mapping the geometry of the animal.
It was a massive conceptual victory. It proved you didn't need one-to-one pixel alignment to learn the underlying mapping between two distinct visual sets.
Right.
But, and this is the crux of why StarGAN had to be invented, there was a crippling core limitation to this pre-StarGAN era. CycleGAN and its contemporaries could only translate between two specific domains at a time.
Horse to zebra.
Summer to winter.
Apples to oranges. Just 2 domains. That was the ceiling. If you wanted to translate apples to oranges and also apples to bananas, you had to build an entirely new, separate model.
And that brings us to the mission of our deep dive today. We are going to explore the core limitation of that 2-domain ceiling. We will unpack exactly how the StarGAN authors shattered it.
They proposed a single model architecture that scales across multiple domains simultaneously.
Yes, and crucially, how they engineered it to bridge completely different, unaligned data sets without breaking the underlying math.
So before we get into the network architecture itself, we should probably define the precise terminology the paper uses.
Good idea.
The authors are very specific about how they categorize visual data, and if we don't lock these terms in now, the later math won't make sense for you as we go along.
The paper leans heavily on three terms: attribute, attribute value, and domain.
Let's start with attribute.
In the context of this paper, an attribute is defined as a meaningful, high-level feature inherent in an image. So if we are dealing with a data set of human faces, which is the primary testing ground for StarGAN, an attribute would be a broad category like hair color, gender, age, or facial expression.
So the attribute is the category itself.
Right?
Because we have the attribute value. I assume that is the specific state or realization of that category.
That is correct. If the attribute is hair color, the attribute values are the specific instances: black, blonde, brown.
Or if the attribute is gender, the values might be male or female. If the attribute is age, the values are young or old.
Exactly.
That leads us to the most critical term, domain. How does a domain differ from an attribute value?
A domain is the actual set of images that share the same attribute value. So if we look at a massive folder of 100,000 photos, all the images of women in that folder represent one single domain. All the images of men represent another domain. All the images of people with blonde hair, regardless of their gender or age, constitute a domain.
I see. So the fundamental goal of multi-domain image-to-image translation is to take an image from one specific domain, say the domain of brown-haired people, and map it into a target domain, say blonde-haired people.
While preserving the underlying identity of the subject, yes.
And doing that across many different domains is where the mathematical bottleneck of the era becomes glaringly obvious.
The StarGAN authors identified this as the inefficiency problem. It's often referred to in the paper as the K times K minus 1 bottleneck.
Let's break that math down. If I'm a researcher in early 2017, and I want to build a system that can translate between K different domains using the CycleGAN architecture, I can't just build one universal translator.
No, because CycleGAN relies on a bidirectional mapping between exactly two spaces. If you introduce a third space, the architecture doesn't know what to do with it.
So what do?
You have to train a distinct independent generator model for every single possible directional pair.
So if K is the number of domains, the number of models I need is K multiplied by K minus 1.
Yes. The paper gives a very concrete, simple example to illustrate the pain of this. Let's say you want to build a system that translates among just 4 domains.
Let's use blonde hair, black hair, male and female. So K equals 4.
To make a complete system that can handle any request among those 4 domains, you need to train 4 times 3 generators.
12?
That is 12 different independent neural networks.
You would need a black hair to blonde hair generator, a separate blonde hair to black hair generator, a male to female generator, a female to male generator, a blonde hair to female generator. It just gets absurd quickly.
It does. 12 massive models just to handle hair color and gender.
Now extrapolate that to a real-world scenario. The paper leans heavily on a very famous machine learning dataset called Celeba, which contains over 200,000 images of celebrity faces.
And Celeba doesn't just label hair color and gender. It provides annotations for 40 distinct facial attributes.
So if a researcher wanted to build a universal facial manipulation tool for the Celeba dataset using the standard cross-domain approach at the time, K is 40.
The math is 40 times 39.
Which results in 1,560 individual generator models.
Imagine walking into your principal investigator's office and pitching that.
Right. I have a great idea for a paper. I just need to monopolize the university's entire GPU cluster for the next 2 years so I can train, manage, and tune the hyperparameters of 1,560 distinct deep neural networks.
It is completely computationally unfeasible. It's an architectural dead end.
The compute cost is staggering. But the StarGAN paper points out a secondary, perhaps more fatal flaw with this multi-model approach.
It isn't just an inefficiency problem. It is a profound data starvation issue.
Data starvation. How can you be starving for data if you are training over 1,000 models on a data set of 200,000 images?
You have to look at what a single one of those isolated models is actually doing during its training loop. Let's zoom in on just one of the 1,560 models. The specific generator tasked with translating brown hair to blonde hair.
Okay.
When that specific neural network is training, what data is it allowed to look at?
By definition, it's a two-domain model, so it's only looking at the domain of brown-haired people and the domain of blonde-haired people.
Exactly. It is entirely blind to the rest of the data set. It never sees the images of people with black hair or red hair or gray hair. It never sees people wearing hats. It never sees bald individuals.
It's restricted.
It is restricted to a small fraction of the total available visual information.
Why does that matter if its only job is to change brown hair to blonde?
Because generating a highly realistic, sharp, convincing human face requires a deep, fundamental understanding of what we call global features.
Like the structure of the face itself.
Yes. A neural network needs to understand the complex geometry of a human jawline. It needs to understand the physics of how light reflects off different tones of human skin. It needs to understand the three-dimensional structure of a nose or how eyes sit in their sockets.
And those global features, noses, lighting, skin texture, are present across all domains, regardless of hair color.
Precisely. By isolating the models into these tiny two-domain silos, you are artificially depriving them of the massive, rich diversity of the full dataset.
So the brown to blonde model has to learn the complex physics of lighting and facial geometry almost entirely from scratch.
Using only its small subset of the data. Meanwhile, the male to female model running on a different GPU is also trying to learn what a nose looks like from a totally different isolated subset of data.
They are doing redundant work.
And they aren't sharing any of that foundational knowledge.
So a model that has seen all 200,000 faces in saliva will simply draw a much better, sharper, more anatomically correct face than a model that has only been allowed to look at 20,000 faces. The data starvation inherently limits the ultimate visual quality of the output.
This realization was the catalyst. The pre-StarGAN landscape was a tangled web of hundreds of isolated, inefficient, data-starved models. The field desperately needed a unified approach.
They needed a way to train one single network on all the data simultaneously.
And that brings us to the core breakthrough of the paper, the star topology.
The authors looked at this web of isolated models and decided to fundamentally rethink the routing.
Instead of building a specific network pathway that only goes from domain A to domain B, they designed a single generator that takes two distinct inputs.
It takes the original image itself, and it takes a target domain label.
The analogy of a language translator works perfectly here. The old CycleGAN approach is like running a massive international conference by hiring hundreds of strictly bilingual translators.
You have one person who only translates English to French. You have another person who only translates French to German.
If you have attendees speaking 40 different languages, you need a small army of 1,560 translators just to cover every possible conversational pairing.
But StarGAN proposes hiring a single, brilliant polyglot.
One master translator who speaks all 40 languages fluently.
You walk up to this polyglot, you hand them a document written in any language, and you hand them a target language flag.
A piece of paper that says, translate this to Japanese.
The polyglot reads the document, looks at the target flag, and outputs the Japanese translation. One person, one model, handling every possible combination dynamically.
It's an incredibly elegant conceptual shift. But conceptual elegance often introduces brutal engineering challenges.
Oh, always.
To build this polyglot neural network, you have to solve a very real architectural problem. How do you actually feed a target domain label into a convolutional neural network, a CNN, that was strictly designed to process images?
This is a fascinating mechanical hurdle. Let's visualize the data structures for a second. The input image, a photograph of a face, is a three-dimensional block of data.
Right.
It has a height, it has a width, and it has depth in the form of three color channels. Red, green, and blue is a spatial tensor.
But the target domain label, that isn't spatial at all. It's just a simple, flat, one-dimensional list of numbers.
It is what we call a one-hot vector or a binary vector.
It's essentially a row of switches. If you have 4 possible domains, your vector is 4 numbers long.
So if you want to instruct the network to generate a blonde person, the vector might look like 0, 1, 0, 0.
Yeah.
Where the one in the second position corresponds to the blonde switch being flipped to the on position.
Right. And you cannot just matrix multiply a flat one-dimensional list of 4 numbers into a dense 3-dimensional image block that is 128 pixels high, 128 pixels wide, and 3 channels deep.
The linear algebra simply does not align. The dimensions are totally incompatible. How did the authors force the network to swallow both inputs simultaneously?
They used a technique called spatial replication.
Spatial replication.
It's a method of expanding non-spatial information so that a convolutional layer can process it naturally. They take that one-dimensional label vector, let's stick with 0, 1, 0, 0, and they physically copy-paste it to match the spatial dimensions of the image.
I want to make sure I'm picturing this correctly. If my input image is 128 by 128 pixels, they take the first number in the vector, the 0, and they create a brand new blank 128 by 128 grid, and they fill every single spot in that grid with a 0.
Exactly. Imagine creating a transparent uniform filter the exact size of your photograph. They create one grid filled entirely with zeros.
Okay.
Then they take the next number, the one representing blonde hair, and they create another 128 by 128 grid filled entirely with ones. They do this for every single element in the label vector.
So if your label vector has n elements, you generate n brand new spatial grids.
And then they perform a depth-wise concatenation.
Depth-wise concatenation is like adding layers to a cake. You take the original red, green, and blue layers of your input photograph, and you stack these new spatially replicated label grids directly behind them.
So if you had a 3-channel RGB image and you have 5 possible domain labels, you concatenate them along the depth axis. Your generator is no longer looking at a 3-channel input.
It is ingesting an 8-channel tensor block.
That is a brilliant workaround. By expanding the label to cover the entire spatial area of the image, it forces every single localized operation within the neural network to be constantly aware of the target instruction.
Right, so when a convolutional filter is scanning over a specific patch of pixels, say the pixels making up the person's nose, it isn't just seeing the colors of the nose.
It is simultaneously reading the spatial label attached to those exact pixels that says, by the way, the overall goal is to make this image blonde.
It integrates the conditional instructions seamlessly into the spatial processing pipeline.
But if you radically alter the generator to become a multi-domain polyglot, you fundamentally break the traditional GAN training dynamic. You have to radically alter the discriminator to keep pace.
Right, because the discriminator in a traditional generative adversarial network is essentially a simple binary security guard. Its only job is to look at an image and make a single classification.
Is this image real or is it fake?
But for StarGAN to function, policing realism is no longer sufficient. The discriminator has to police accuracy.
Because the generator could produce an absolutely flawless photorealistic image of a person with black hair.
And the traditional discriminator would look at it, say, this looks perfectly real, and pass it.
But if the input label specifically requested blonde hair, the generator has actually failed the task. To solve this, the StarGAN authors leveraged the concept of auxiliary classifiers. They evolved the discriminator into a multitasking network. Instead of outputting a single probability, the StarGAN discriminator outputs 2 distinct parallel probability distributions.
Let's break those down. First, it outputs a probability distribution over the image sources.
This is the traditional GAN task. It evaluates the texture, the lighting, the structure, and outputs a score indicating whether the image is a real photograph or a synthetic fake generated by the network.
But simultaneously, through a separate output branch connected to the same deep feature layers, it outputs a probability distribution over the domain labels.
It acts as a classifier. It looks at the image and tries to answer, does this person have blonde hair? Are they male? Do they look young?
This dual output mechanism is what provides the necessary feedback loop to train the generator.
The generator now has 2 masters to satisfy. It must produce an image that looks real enough to fool the source discriminator, and it must produce an image that contains the correct attributes to satisfy the domain classifier.
Which serves as the perfect bridge into the mathematical engine room of the paper. We need to unpack the objective function.
An objective function is essentially the grading rubric for the neural network.
It's the mathematical formula the model uses to calculate its loss, or how wrong it currently is. During training, the network's only goal is to adjust its internal weights and biases to drive that loss number as close to 0 as possible.
The objective function in StarGAN is exceptionally robust, and it is built upon 3 distinct mathematical pillars. Let's start with the first, and arguably the most notoriously difficult pillar to tune: the adversarial loss.
Denoted as LADV.
This is the classic cat-and-mouse game that defines all GANs. The generator, G, takes an image and a target label and generates a fake output. It wants that fake to be indistinguishable from reality.
And the discriminator, D, looks at real images from the dataset and fake images from the generator and tries to learn the difference.
The discriminator is constantly updating its weights to become a better detective, and the generator is constantly updating its weights to become a better counterfeiter.
But anyone who has ever tried to train a standard GAN knows that this cat-and-mouse game is highly unstable. It rarely proceeds smoothly.
Why is it so unstable?
If they're both learning from each other, shouldn't they eventually reach a perfect equilibrium?
In theory, yes. In practice, the gradients, the directional signals that tell the networks how to update their weights, can become utterly useless. The most common failure mode is called mode collapse.
Mode collapse.
Imagine the generator discovers one single specific arrangement of pixels, say, a blurry, vaguely face-like blob that somehow tricks the current version of the discriminator.
Instead of learning how to draw a variety of distinct realistic faces, the generator realizes, hey, this one blurry blob works every time.
So it stops learning. It just outputs that exact same blob over and over again, regardless of the input. It collapses all its outputs into a single mode.
And standard GAN loss functions, which often rely on Jensen-Shannon divergence to measure the difference between the real and fake data distributions, fail to provide a useful corrective signal when the distributions don't overlap.
If the generator's fake images are terrible, the standard loss just says, you are wrong, but it doesn't provide a clear mathematical path on how to get better. The gradients vanish.
So, to stabilize this chaotic training dynamic, the StarGAN authors completely abandoned the standard GAN loss. They swapped it out for something called the Wasserstein-GAN objective with gradient penalty.
Commonly abbreviated as WGAN-GP.
This was a critical architectural choice. WGAN-GP replaces the concept of divergence with the Wasserstein distance,
which is often intuitively described as the Earth mover's distance.
The Earth mover analogy is fantastic. Can you walk through how that works in this context for our listeners?
Imagine the distribution of real facial images in your dataset is a giant, complexly shaped pile of dirt, and the distribution of the fake images your generator is currently producing is another, completely separate pile of dirt.
Okay, 2 piles of dirt.
The standard GAN loss tries to measure the mathematical overlap between these piles. If they are far apart, the overlap is 0, and the learning signal dies.
And the Earth mover's distance measures something different.
It measures the minimum amount of physical work required to move the dirt from the fake pile and reshape it until it perfectly matches the real pile.
Exactly. Even if the fake pile is miles away from the real pile, meaning the generated images look nothing like real faces, there is always a measurable, continuous cost to move that dirt.
Because the distance is continuous, it provides a smooth, meaningful gradient. It constantly gives the generator a clear directional signal. Move your pixel distribution this way to get closer to reality.
It prevents the learning process from stalling out.
And what about the GP part, the gradient penalty?
Right. For the Wasserstein distance mathematics to hold true, the discriminator, which in WGANs is technically called a critic, must adhere to a strict mathematical constraint called the one-Lipschitz continuity.
Simply put, it means the discriminator's gradients cannot be allowed to explode and grow infinitely large. The gradient penalty is an extra term added to the loss function that penalizes the discriminator if the norm of its gradient deviates significantly from 1.
It essentially puts a speed limit on the discriminator, ensuring it acts as a stable, reliable judge rather than wildly changing its criteria every batch. By adopting WGAN-GP, the authors ensured their single polyglot generator wouldn't crash into mode collapse while trying to learn multiple domains simultaneously.
So that is pillar 1. The adversarial loss guarantees the generated image looks like a real photograph, but it does absolutely nothing to guarantee that the image matches the requested attributes.
That is the job of pillar 2, the domain classification loss, denoted as LCLS.
This pillar utilizes the second branch of that multitask discriminator we discussed earlier. The objective here is to ensure that if I input a label requesting blonde hair, the final image actually has blonde hair.
The paper details that this loss is calculated in 2 distinct alternating training phases. Let's look at phase 1, training the discriminator.
During this phase, you isolate the discriminator. You feed it real images drawn directly from the training dataset, and you pair those images with their true, known ground truth labels.
So you show the network a high-resolution photograph of a blonde celebrity from the Celeba dataset, and you provide a label vector that explicitly says, this image is blonde, this image is female, this image is young.
The discriminator processes the image, makes its predictions across all the domains, and then calculates the error between its predictions and the true labels using standard cross-entropy loss.
It backpropagates that error to update its own internal weights.
Over thousands of batches, this branch of the discriminator becomes an absolute expert at identifying what blonde or male or angry actually looks like in real photographic data.
Once the discriminator is properly calibrated, the training loop flips to phase 2, training the generator. In this phase, the generator takes an input image and a randomly generated target label, say, make this person look old, and generates a fake image.
That fake image is then passed to the discriminator. The discriminator analyzes it and outputs its classification predictions.
And here's where the feedback loop closes. If the generator produces a stunningly realistic image, but the person still looks young, the discriminator will classify it as young.
The generator receives a massive penalty to its domain classification loss because it failed to satisfy the target condition.
To minimize this loss, the generator is forced to adjust its weights to actually apply the requested attribute in the next iteration.
It creates a beautiful synergy. Pillar 1 forces the image to be realistic. Pillar 2 forces the image to be accurate to the label.
But mathematically speaking, there is still a massive loophole that these two pillars do not close.
Let's explore that loophole because it highlights a fundamental problem in unconstrained generative models. Let's say I take a photograph of myself, I feed it into the generator, and I provide a target label requesting blonde hair and male.
What stops the generator from completely ignoring your input photograph and simply outputting a perfectly memorized high-resolution photograph of Ryan Gosling?
Exactly. If the generator outputs Ryan Gosling, it satisfies pillar 1 entirely. The image is a real photograph of a human. The discriminator will say, real.
It also satisfies pillar 2 entirely. Ryan Gosling is blonde and male. The classification branch will say blonde and male. The generator would theoretically receive a perfect score and 0 loss.
But from a user perspective, the model has completely failed the task. The goal is image-to-image translation.
It is supposed to translate your face, modifying only the specific attributes requested. It is not supposed to hallucinate an entirely new identity.
The network needs a mathematical constraint to guarantee that the underlying structure, the geometry, the identity, the soul of the original image is preserved.
And this brings us to pillar 3, the most conceptually fascinating piece of the objective function, the reconstruction loss, denoted as LREC.
Which is driven by the concept of cycle consistency.
Cycle consistency is an elegant concept that was the defining feature of CycleGAN, and the authors of StarGAN adapted it brilliantly for a unified, multi-domain architecture.
The intuitive premise is simple. True translation should be perfectly reversible.
If I take a complex legal document written in English, and I hire a translator to convert it to French, how do I verify the translation is accurate if I don't speak French?
You hire a second, independent translator to take that French document and translate it back into English.
If the twice translated English document matches my original English document word for word, I can be highly confident that the core meaning was preserved during the intermediate French stage.
If the second document is totally different, you know the first translator hallucinated or lost information. StarGAN applies this exact logic to pixels.
Let's trace the forward and backward pass explicitly. The generator takes your original input image, let's call it X. It pairs X with the target domain label, let's say blonde. It processes the image and outputs a fake translated image Y.
That is the forward translation. Now, the model takes that newly generated fake image, Y, and fills it right back into the exact same generator.
But this time, it provides the original domain label of image X as the target instruction.
So if you originally had brown hair, it takes the fake blonde image and gives the generator the instruction, take this blonde person and make their hair brown.
It forces the generator to perform the inverse operation. The image has now been translated twice, out and back again. Let's call this twice translated, reconstructed image X reconstructed.
The network then mathematically compares the original image X with the reconstructed image X reconstructed.
And they measure this difference using an L1 norm. What exactly is an L1 norm in the context of image tensors?
The L1 norm, also known as mean absolute error, is a very straightforward pixel by pixel comparison. The algorithm looks at the pixel at coordinate 1 in the original image and the pixel at coordinate 1 in the reconstructed image.
It subtracts the color values and takes the absolute value of the difference.
It does this for every single pixel across all 3 color channels and sums the errors up.
So if the reconstructed image is perfectly identical to the original image, the L1 loss is exactly 0.
But let's go back to our Ryan Gosling loophole. If the generator took your input photo, ignored your facial geometry, and just output Ryan Gosling, what happens during the reverse cycle?
The generator takes the Ryan Gosling image and is told to make him have brown hair. It will output a picture of Ryan Gosling with brown hair.
Then the L1 norm compares your original face with a brown-haired Ryan Gosling.
The pixel values for the shape of the jaw, the distance between the eyes, the background scenery, everything will be wildly different.
The L1 loss will absolutely explode.
This massive penalty forces the generator to realize that it cannot just hallucinate new identities.
The only way for the network to successfully cycle back to the original image and minimize the L1 loss is to leave the background, the clothing, and the underlying facial geometry completely untouched during the forward translation.
It forces the network to only manipulate the specific pixels required to change the targeted attribute.
The authors were acutely aware of how critical this constraint was. You can see it in how they tuned the hyperparameters of the final full objective function. They didn't just add the three pillars together equally. They weighted them.
The adversarial loss serves as the unweighted baseline. The domain classification loss, controlled by a hyperparameter called lambda CLLs, is given a weight of 1.
But the reconstruction loss, controlled by lambda rec, is weighted at 10.
A factor of 10. By setting lambda rec to 10, they are explicitly programming the network's priorities.
They are telling the generator, we care 10 times more about you preserving the core identity and spatial structure of the input image than we do about you perfectly hitting the target attribute.
If they had set the weight to 1, the model might learn to severely distort the face just to make the hair slightly blonder. The heavy penalty ensures identity preservation is the supreme rule of the network.
All right, we have a firm grasp on the objective function, the grading rubric that guides the learning. Now let's lift the hood and look at the actual physical structure of the network that is doing the processing.
The authors are very transparent that they did not try to reinvent the wheel when it came to the layer-by-layer topology of the generator. They heavily adapted the structural design from CycleGAN, which had already proven to be a highly robust architecture for extracting and manipulating image features.
The generator processes the input tensor in 3 distinct stages. Let's walk a tensor through the pipeline. The first stage is downsampling.
The network takes the input image, which, remember, has been concatenated along the depth axis with those spatially replicated domain labels, and passes it through 2 convolutional layers. Crucially, these layers use a stride of 2.
What does a stride of 2 accomplish mathematically?
In a standard convolution, the filter slides over the image 1 pixel at a time. With a stride of 2, the filter jumps 2 pixels at a time. This effectively halves the spatial dimensions, the height and the width of the feature map at each layer.
So a 128 by 128 image becomes 64 by 64 and then 32 by 32.
But while the spatial dimensions are shrinking, the depth, the number of feature channels is increasing. It's taking the raw, high-resolution pixel data and compressing it down into a much denser, richer, lower-dimensional representation.
It is extracting the semantic meaning, the high-level concepts, from the raw pixels.
Once the image is compressed into this dense conceptual block of features, it enters the second stage, the bottleneck.
This is the core engine of the generator, consisting of 6 consecutive residual blocks.
Residual blocks were famously introduced in the ResNet architecture, which won the ImageNet competition in 2015. Why are they so critical for an image translation task?
Before ResNets, deep networks suffered from the vanishing gradient problem. As you added more layers, the learning signal would degrade as it passed backward through the network until the early layers stopped learning entirely.
Residual blocks solve this by using skip connections.
Instead of forcing a layer to learn a completely new transformation from scratch, a skip connection takes the input to the block and literally adds it directly to the output of the block.
The layer is only forced to learn the residual, the specific changes or tweaks it needs to apply to the input.
In the context of StarGAN, these 6 residual blocks are where the actual translation magic happens. Because of the skip connections, the network can easily say, hey, most of this dense feature map representing the nose and the background is perfectly fine as it is. Just let it pass through. I only need to tweak these specific feature channels that control hair color.
It allows for deep, complex manipulation without corrupting the untargeted features.
After passing through the bottleneck, the translated feature maps enter the third and final stage, upsampling.
The network takes these manipulated, dense conceptual features and passes them through 2 transposed convolutional layers. These act like reverse convolutions.
They expand the spatial dimensions back up, step by step, from 32 by 32 back to 64 by 64, and finally output a full-resolution 128 by 128 image that perfectly matches the dimensions of the original input.
But there is a vital, highly specific architectural detail here that we absolutely cannot gloss over. Throughout the generator, after every single convolutional layer, the authors apply a normalization technique.
But they don't use batch normalization, which is the industry standard for almost all classification networks. They explicitly use instance normalization.
This is a crucial distinction. To understand why instance normalization is the secret sauce for image translation, we have to understand why batch normalization fails at it.
Let's define batch norm. During training, you don't feed images into a network one by one. You feed them in batches, say 16 images at a time to maximize GPU efficiency.
Batch normalization looks at the feature activations across all 16 images in that batch. It calculates the mean and the variance for the entire batch, and then normalizes the data based on those collective statistics.
It centers the data and makes training incredibly stable, but it mathematically ties the 16 images together.
In an image translation task, especially when you are doing style transfer or altering facial attributes, the style of an image, its overall contrast, its specific brightness, the unique texture of the skin, is deeply encoded in the specific mean and variance of its own internal feature maps.
Ah, I see the problem. If you have a batch of 16 totally different faces, some dark, some light, some highly contrasted, some soft, and you calculate an average mean and variance across all of them, you are mathematically washing out the unique stylistic information of each individual face.
You are averaging away the very details you are trying to preserve or manipulate.
Exactly. Batch normalization creates a stylistic bleeding effect between the images in the batch.
Instance normalization, on the other hand, normalizes the data across the spatial dimensions of an individual image, channel by channel.
It calculates the mean and variance for image 1 and normalizes image 1. It calculates separate statistics for image 2 and normalizes image 2. It completely ignores the rest of the batch.
This isolates the images. It strips away the specific contrast and stylistic artifacts of the input image on a per-instance basis, providing a clean, normalized slate for the residual blocks to apply the new target style to, without being contaminated by the statistical noise of the other 15 images currently sitting in the GPU memory.
It is an elegant application of linear algebra to preserve visual fidelity. And speaking of visual fidelity, we have to look at the architecture on the other side of the adversarial game, the discriminator.
We established earlier that it's a multitask network, but structurally it doesn't look at the image the way you or I do. It uses a patch-GAN architecture.
Patch-GAN is a fascinating departure from traditional classification networks. Usually a discriminator ingests an entire image, processes it through fully connected layers, and outputs one single probability score for the entire picture.
This whole image is 90% likely to be real.
But a patch-GAN discriminator doesn't output a single number. It outputs a two-dimensional grid of values, for example, an n by n matrix.
How does a grid evaluate realism?
Each individual value in that output grid represents the discriminator's verdict on a specific, localized patch of the original image. By carefully designing the convolutional layers and avoiding fully connected layers, the network creates a specific receptive field.
A single value in the output grid might trace back mathematically to a 70 by 70 pixel square of the input image.
So instead of a single security guard looking at the whole painting, patch-GAN is like an army of critics, each holding a magnifying glass, scanning a specific 70 by 70 pixel patch, and rendering a verdict on just that patch.
Is this patch of skin real? Is this patch of background real? Is this patch of hair real?
The reason this is absolutely critical for StarGAN comes back to the L1 reconstruction loss we discussed in Pillar 3.
The L1 norm is fantastic at preserving the low-frequency global structure of an image, the overall shape of the head, the general color of the shirt.
But L1 loss notoriously struggles with high-frequency details. It tends to average out sharp edges, resulting in blurry, soft images.
Because mathematically, a slightly blurry edge has a lower absolute error than a perfectly sharp edge that is misaligned by a single pixel.
Precisely. The patch-GAN discriminator acts as a high-frequency enforcer. By forcing the generator to ensure that every single localized patch of the image looks indistinguishable from a real photograph, it forces the network to hallucinate and render incredibly sharp, high-frequency details.
It's the architectural choice that ensures the generated skin has visible, realistic pores, that the lighting catches the moisture on the lips, and that the generated hair has individual distinct strands rather than just looking like a smooth plastic blur.
So if we step back, we have this incredibly robust, well-engineered star topology. We have spatial replication to feed the labels, WGAN-GP for stability, cycle consistency to preserve identity, and PatchGAN to enforce crisp details.
It works beautifully on a massive, densely labeled dataset like Saliba. But the authors didn't stop there. They pushed the architecture into entirely new territory.
Which brings us to what I consider the true Hall of Fame innovation of this paper, training across multiple, completely unaligned datasets.
The authors wanted to achieve a capability that had never been demonstrated before. They wanted their single polyglot model to be a master of everything.
They wanted to train it on the Saliba dataset, which provides 40 labels focusing on physical traits like hair color, gender, and age. But simultaneously, they wanted to train it on a completely different dataset called RayFD.
RayFD stands for the Red Boot Faces Database. It's a much smaller dataset, typically photographed in a sterile lab environment, but it contains something Saliba lacks entirely: highly accurate facial expression labels.
Happy, angry, fearful, disgusted, neutral.
The dream is to have a model that can take a highly complex celebrity face from Saliba and make them look fiercely angry using the specific muzzle movement knowledge it learned from the RFD dataset, a true crossover translation.
But here's the massive roadblock. The datasets are completely, fundamentally unaligned.
Saliba does not have expression labels. A celebrity on the red carpet might be smiling brilliantly or scowling at paparazzi, but the dataset simply doesn't contain a label for it.
Conversely, RFD does not have labels for hair color or attractiveness or wearing a hat.
If you think about the architecture we just painstakingly described, this missing data is a showstopper. Why? Because of the cycle consistency loss.
Let's trace the loop again to see where it breaks. I feed a smiling Saliba image into the network. I provide a target label from the RFD domain, make this person angry.
The forward pass works fine. The generator outputs an angry celebrity, but now I have to cycle back. I have to feed the angry celebrity back into the generator to reconstruct the original image.
And what target label do you give the generator to cycle back? You need to give it the original label, but you don't know what the original expression was because Saliba doesn't label expressions.
If I don't give it a label, the network doesn't know what to do. If I just guess and say neutral, but the original photo was actually a massive smile, the generator will reconstruct a neutral face.
The L1 loss will compare a neutral reconstruction against a smiling original. The mathematical difference will be massive. The loss will explode, the gradients will corrupt, and the network will completely fail to learn.
The missing labels fundamentally break the entire training loop.
It's an intractable problem under standard architectures. How do you calculate error when you don't know the ground truth? The StarGAN authors solved this with a brilliantly simple yet profoundly impactful concept they call the mask vector.
Denoted mathematically as M. How does the mask vector work? It sounds like it must be a highly complex dynamic algorithm to handle unaligned data streams.
The beauty of it is its absolute simplicity. It is an n-dimensional one-hot vector, where n simply represents the total number of distinct data sets you are training on. Since they are combining two data sets, Saliba and RFDN is 2.
So the mask vector is literally just two numbers. It is 1, 0 if the input image originates from the Saliba dataset, and it is 0, 1 if the input image originates from the RayFD dataset. It's just a binary flag.
Exactly. They then create a unified master label vector that concatenates everything together. The new input fed into the generator is a long list. The 40 Saliba labels, immediately followed by the 8 RAFD labels, immediately followed by the 2-digit mask vector.
But we still haven't solved the missing data. If the image is from Saliba, we have the 40 Saliba labels. But what do we put in the slots for the 8 RAFD expression labels?
They hardcode them to absolute 0. If the mask vector is 1, 0 indicating Saliba, the entire section of the input vector dedicated to RFD expressions is forced to 0, 0, 0, 0, 0, 0, 0, 0.
Okay, I have to push back here because intuitively, this sounds like a terrible idea. If I'm training a neural network and I constantly feed it images of smiling, expressive celebrities, but I explicitly label all of their expressions with hard zeros, won't the network just associate 0 values with smiling faces? Doesn't the network get completely confused and learn that Saliba people are permanently emotionless?
That is exactly what would happen in a standard network. But the mask vector fundamentally alters the learning dynamics. It acts as a dynamic routing switch. During training, the network is presented with alternating batches of Saliba data and RFD data.
When the generator processes a Saliba batch, it sees the mask 1, 0. It processes the image, calculates its losses, and updates its weights. When it processes a RFD batch, it sees the mask 0, 1, and sees the Saliba labels zeroed out.
Through thousands of iterations of this alternating process, the gradient descent algorithm naturally figures out the correlation. The network learns that when the mask is 1, 0, any signal coming from the RFFD section of the vector is mathematically useless noise. It contributes nothing to minimizing the loss.
Therefore, the network adjusts its internal weights to dynamically shut off its attention to those specific input channels based entirely on the state of the mask.
It learns to ignore the zeros. It focuses exclusively on the explicitly known valid labels that are confirmed by the mask vector.
And crucially, the discriminator is programmed with the same logic. When the discriminator processes a fake image generated from a Celeba input, it looks at the mask vector.
Seeing 1, 0, the discriminator only calculates the classification error for the 40 Celeba attributes. It completely bypasses the expression classification branch for that specific batch.
It doesn't penalize the generator for failing to classify an expression because it knows that information isn't mathematically valid.
That is astonishing. By implementing this simple routing mechanism, they created a system where these disparate data streams can flow through the exact same deep convolutional weights without corrupting each other.
The network learns low-level, global features, eyes, noses, skin textures from the massive volume of the Celeba dataset.
Yeah.
Simultaneously, it learns the specific, localized geometric changes required to make those features mimic expressions from the smaller RFID dataset.
It builds a shared, universal, latent representation of a human face, drawing the best information from each dataset. And the authors designed a brilliant forensic experiment to prove conclusively that the network had internalized this logic.
It's detailed in Figure 7 of the paper, often referred to as the wrong mask experiment.
This is my favorite part of the paper because it's like a psychological test for an AI. What exactly did they do?
During inference, when the model is fully trained and just running predictions, they took a random celebrity image from Celeba. The correct mask for this image should be 1, 0. But they actively lied to the model.
They appended the RFD mask vector 0, 1 to the Celeba image.
They are essentially telling the polyglot, translate this document using the strict grammar rules of RayFD.
Yeah.
What happens when you feed a network conflicting data like that? Does the forward pass crash? Does it output static noise?
No, it processes the image. It tries to apply a facial expression as dictated by the RFD mask, but it fails to synthesize the expression correctly. The face looks somewhat distorted.
But what is truly fascinating is the unintended side effect. Without being explicitly asked to do so, the network drastically manipulates the age of the input image. It makes the celebrity look significantly older.
Why on earth would giving it the wrong dataset flag cause it to age the person?
It perfectly reveals the network's internal logic. Remember, because the mask was artificially set to ORAFD, the network has been trained to treat the Celeba section of the label vector as uninformative zeros. It looks at the actual Celeba labels provided, but the routing switch says, treat these as zeros.
And in the specific encoding of the Celeba dataset, age is tracked as a binary attribute labeled young. A 1 means the person is young. A 0 does not mean neutral. A 0 explicitly means not young, which the network interprets as old.
Exactly. By forcing the network to interpret the Celeba vector as zeros via the wrong mask, the model automatically processed the instruction as, regardless of what this person actually looks like, ensure the young attribute is set to 0.
It dutifully translated the face to look old.
It's beautiful. It proves beyond a shadow of a doubt that the model wasn't just memorizing inputs or blindly applying filters. It had deeply learned the semantic meaning of the mask vector, dynamically routing its internal feature processing based on that simple 2-digit flag.
With the architecture and the multi-dataset routing completely solidified, we can examine the experimental results. How did StarGAN actually stack up against the reigning champions of 2017?
Let's briefly outline the training parameters. For Celeba, they used 128 by 128 pixel crops of the faces, setting aside a dedicated block of 2,000 images purely for testing. They focused on translating across 7 specific domains: black hair, blonde hair, brown hair, male, female, young, and old.
For ROPDV, they also used 128 by 128 crops, utilizing the 8 expressions captured across 3 different camera angles.
They pitted StarGAN against 3 specific baselines: DIAT, CycleGAN, and IGAN. We've discussed CycleGAN and IA. Those are the isolated point-to-point 2-domain models that require training hundreds of separate networks.
IGN operates on a fundamentally different principle.
How does IGAN work, and why did the StarGAN authors include it as a baseline?
IGAN uses an encoder-decoder architecture. It takes the high-resolution input image and passes it through an encoder network that compresses all the visual data into a tiny, low-dimensional, one-dimensional latent vector.
It attempts to learn an inverse mapping, disentangling the attributes within that highly compressed latent space, changing the desired attribute, and then using a decoder network to expand that modified vector back into a full image.
When we look at the qualitative supremacy, the actual visual quality of the output images provided in the paper's figures, StarGAN operates on an entirely different level of realism. Let's contrast it with IGAN first.
The visual results for IGAN are jarring. If you feed it a picture of a female celebrity and ask it to change her hair color, it frequently outputs a picture of a completely different person. Sometimes it even generates a male face when asked to modify a female input. It completely fails to preserve personal identity.
The architectural reason for this failure traces directly back to that encoder bottleneck. When you take a 128 by 128 image and mathematically compress it into a tiny 1D vector, you inherently destroy the fine spatial geometry.
The precise millimeter distance between the eyes, the exact curve of the cheekbone, the specific asymmetry of a smile, it is all lost in compression. The decoder is essentially guessing the facial structure from a generalized summary.
And StarGAN avoids this because it never compresses the image into a 1D vector. Because StarGAN utilizes fully convolutional activation maps and those crucial skip connections in the residual blocks, the 2D spatial geometry of the face is retained and passed forward throughout the entire translation process.
The structural integrity is never broken.
So WGAN fails on identity preservation. What about CycleGAN and DIAT? They are built on convolutional networks, so they preserve identity much better. However, their outputs are consistently noticeably blurry. They lack crispness, and they frequently introduce strange artificial artifacts into the background.
And this brings us full circle back to the very first problem we discussed, data starvation. CycleGAN and DIAT are strictly two-domain models. If they are training to translate a happy expression to an angry expression on the raw FD dataset, they're only allowed to look at the 500 happy images and the 500 angry images.
They train on 1,000 images total.
StarGAN, by virtue of its unified topology, trains on all the domains simultaneously. During its training loop, it sees the happy faces, the angry faces, the sad faces, the fearful faces, the surprised faces. It leverages implicit data augmentation.
It is learning from 4,000 images.
Because it is exposed to 4 times the data, its convolutional filters learn a fundamentally superior, sharper, more universally accurate understanding of what a human face looks like, completely independent of the specific expression it is currently trying to synthesize. The data efficiency translates directly into visual sharpness.
Of course, researchers can be biased when selecting images for a paper. The authors knew they couldn't just rely on cherry-picked visual examples. They backed up their qualitative claims with rigorous quantitative results using AMT user studies.
AMT stands for Amazon Mechanical Turk. It is a crowdsourcing platform where researchers can pay human workers to perform tasks that computers struggle with. In this case, evaluating the perceptual realism of an image. They set up blind A, B, C, D tests.
A human worker is shown an input image and 4 generated outputs from the different models, randomized so they don't know which model generated which image.
They asked to vote on 3 criteria. Which image looks the most realistic, which one best applied the requested attribute, and which one best preserved the original identity.
The survey data is a landslide. Across almost every metric, StarGAN dominated human preference. But the most telling data point emerges when they tested complex multi-attribute transfers.
This is where they really flex the multitask nature of the architecture. They asked the models to take a single input image and change the hair color and the gender and the age, all simultaneously in one single pass.
For a point-to-point model like CycleGAN, executing a multi-attribute transfer requires feeding the image through 3 separate sequential networks. You run it through the hair generator, take that output, feed it into the gender generator, take that output, and feed it into the age generator.
And every time you pass an image through a GAN, you introduce slight errors and artifacts. By the 3rd pass, those errors compound exponentially, resulting in a degraded, blurry mess. But StarGAN does it all in one unified step. The polyglot applies all the grammatical rules at once.
In the AMT survey for this complex simultaneous translation task, StarGAN captured 52.2% of the total human votes. Over half the time, humans explicitly chose StarGAN's output as the superior image.
Let's look at the competitors. DIAT received 15.6% of the vote. CycleGAN received 11.9%. Again, received 20.3%. StarGAN isn't just marginally better, it is crushing the established state-of-the-art architectures by a factor of 3 or 4 in multi-domain tasks.
It decisively proved that the unified topology was not just more efficient. It was inherently more capable of handling complex, intersecting visual logic. But we cannot close the book on the experimental results without delivering the final, most staggering metric of the entire paper.
We have to talk about parameter efficiency.
This is the absolute mic drop of the paper. Let's look at the compute required to learn all the possible multidirectional translations on the RFD expression dataset.
Because of the k times k minus 1 bottleneck, DIAT required training and maintaining 7 separate generator networks. CycleGAN, due to its bidirectional nature, required 14 separate models to cover the entire domain matrix.
Each one of those individual CycleGAN models contain roughly 52.6 million trainable parameters. So to deploy a full CycleGAN system for this dataset, you are managing 52.6 million parameters multiplied by 14.
That is over 736 million parameters. The memory footprint is massive.
StarGAN required exactly one model, and that single unified generator contained 53.2 million parameters.
It achieved state-of-the-art results, dominated human preference studies, and rendered sharper, higher-quality images while utilizing up to 14 times fewer parameters than the leading alternatives.
It didn't win by utilizing massive server farms to throw brute force compute at the problem. It won by being radically, structurally smarter about how it routed data through its parameters.
Which perfectly sets up the final phase of our deep dive: lasting influence and legacy. This parameter efficiency, this unified topology, it wasn't just a neat parlor trick for changing hair color. It represented a fundamental paradigm shift for the entire field of machine learning.
Prior to the publication of papers like StarGAN, the prevailing philosophy in artificial intelligence was strict specialization. If you have a specific, defined task detecting cancer in an X-ray, translating English to French, changing summer to winter, you build a highly specialized, custom-tailored, point-to-point architecture specifically optimized for that exact task.
StarGAN provided compelling mathematical proof that pushed the field toward the philosophy of unified, generalized architectures.
It proved the concept that training a single network on more diverse tasks simultaneously acts as a powerful regularizer that actually improves baseline performance across all tasks.
That specific idea is the core foundational tenet of modern machine learning.
Exactly. When you force a single network to learn how to translate hair color and age and gender and facial expressions all at once, the network cannot afford to memorize superficial tricks. It is forced to learn a much deeper, more robust, mathematically fundamental representation of reality.
This exact same philosophy is visible in everything we do today. Think about modern large language models.
We don't train a separate 50 billion parameter LLM solely for writing Python code, and a different model for translating French, and a different model for summarizing legal documents.
We train one massive, unified, foundational model on a corpus containing all of those tasks. The joint training makes the model better at Python because its logical reasoning was improved by learning French grammar.
StarGAN was demonstrating the power of this unified joint training concept in the visual domain years before it became the industry standard in natural language processing.
However, as with all historic seminal papers, we have to look at it objectively, acknowledging the author's limitations and the benefit of our own hindsight.
Revolutionary as the star topology was, it was not the final word in image generation.
No, it wasn't. We have to acknowledge the resolution constraint. The paper primarily operates at 128 by 128 pixel resolution, with some results generated at 256 by 256 in the appendix.
While the images are remarkably crisp for that specific resolution, generating true megapixel quality, high-resolution images using this exact architecture proved exceedingly difficult.
The bottleneck was the very thing that made it work. The strict L1 cycle consistency loss. Calculating pixel by pixel absolute error over millions of pixels becomes computationally unwieldy.
More importantly, cycle consistency enforces a strict mathematical bijection. It assumes that every single detail can be perfectly preserved and perfectly reversed.
And in the real world, complex image translation is rarely a perfect bijection. If you translate an image of a person with a short buzz cut into a person with flowing shoulder-length hair, the generator has to cover up the background behind the new hair.
When you cycle back to the buzz cut, the generator has to perfectly reconstruct the specific background details, the books on a shelf, the leaves on a tree that were hidden by the long hair.
It requires the network to hallucinate information from nothing, or to perfectly remember destroyed information. Cycle consistency mathematically struggles when spatial information needs to be fundamentally created or destroyed rather than just shifted.
This inherent limitation paved the way for subsequent iterations. The authors themselves released StarGAN v2, which introduced style codes for more diverse, unconstrained outputs.
And eventually the field underwent another massive paradigm shift, moving away from GANs entirely for high-fidelity generation, embracing the probabilistic noise-denoising approach of diffusion models.
But the architectural DNA forged in this paper, the use of conditional routing vectors, the single-generator multi-domain scaling, the concept of spatial replication, that DNA is permanently embedded in the foundational history of neural network design.
It is a masterclass in looking at a brutal mathematical bottleneck and solving it not with more compute, but with a more elegant topology.
Okay, we have thoroughly unpacked the math, the architecture, and the legacy. It is time for our outro, and you know what that means.
It is time for the Novel Notions segment.
I have my notebook ready.
Now, before we proceed, a very important disclaimer for our audience. The following segment is for entertainment purposes only. The ideas we are about to discuss are highly speculative, currently untested, and actively push the boundaries of scientific validation. Do not base your PhD thesis or your startup pitch deck solely on a podcast segment without rigorous peer review and mathematical simulation.
Consider yourselves thoroughly warned. What are the rules of engagement today?
The rule is simple. We limit ourselves to pitching one or two outlandish yet logically consistent new research ideas inspired directly by StarGAN's legacy. We are going to project extreme futuristic scenarios based specifically on the paper's core technical mechanisms.
Today, we are focusing on the mask vector's ability to bridge unaligned datasets and the concept of multi-domain cycle consistency.
I love this constraint.
What do you have for idea one?
I call idea one star LLM, continuous cross-modal translation via mask vectors.
Okay, you are taking the StarGAN architecture out of the visual realm entirely and moving it into sequential data. What is the core concept?
What if we take the mask vector concept, this incredible ability to stitch together entirely unaligned, disparate datasets simply by routing unknown labels to zero, and apply it to a massive transformer network processing completely different sensory modalities?
Imagine a single, continuous, latent space where the domains aren't visual attributes like hair color or facial expressions. The domains are massive, isolated, completely unpaired datasets. Let's use natural language text, seismic tectonic wave data, human fMRI brainwave recordings, and high-frequency financial tick data.
That is a violently chaotic mix of data. Usually, if you want to train a model to translate between domains like that, say, for a brain-computer interface, you require strictly paired data. You need a human subject sitting inside an fMRI machine, actively thinking the word apple, while the text label apple is recorded exactly in time with the brainwave spike.
Exactly. The paired data bottleneck again. But what if we don't have that paired data? What if we just have a massive database of raw human fMRI thought patterns recorded during various daily activities, a completely separate database of robotic motor execution commands, and a massive text corpus from the internet?
The bridging mechanism here is the mask vector. We use a unified conditional vector for the transformer. Let's format it as ctext, cFRI, cmotor.
So if you feed it a batch of text, the mask M flags it as text, and the fMRI and motor labels are zeroed out. The network processes the sequential text data. Next batch is fMRI data. The text labels are zeroed out.
Precisely. The mask vector allows us to jointly train a massive transformer on these totally disparate data sets using a StarGAN-style cycle consistency objective function.
The network is forced to find a universal underlying mathematical representation of sequential patterns. It learns the grammar of seismic waves, the grammar of fMRI, and the grammar of human language, all entangled within the exact same massive weight space.
And the scenario. What is the first experiment you run once this massive star LLM is trained?
The goal is true, unaligned cross-modal translation. I want to translate a human fMRI thought sequence directly into a robotic motor command or a string of text without the network ever having seen a single paired example of thought-to-robot data in its training life.
You input an fMRI sequence, set the target domain flag to text, and execute the forward pass.
The cycle consistency loss ensures that the underlying semantic intent or geometry of the brainwave sequence is preserved as it is mathematically mapped into the latent space of language.
It's effectively bridging human cognition and machine execution using purely unaligned data relying on the assumption that complex systems share universal underlying topologies.
It's audacious. You're betting that the underlying mathematical topology of human thought shares enough geometric similarity with the topology of language that a star topology network could align them implicitly, simply by being forced to cycle between them. The L1 loss of the mind. I love the ambition. My turn for idea 2.
Let's hear it. Lay it out.
Idea 2. Temporal cycle consistency for material degradation simulation.
Oh, moving from facial attributes in human thought into the realm of hard physics and time.
Exactly. We are taking StarGAN's cycle consistency, that LREC loss that enforces identity preservation, and we are applying it over a strict temporal axis to predict structural decay in metallurgy.
The concept here is that instead of domains being categorized as blonde or aged, the domains are defined as specific physical states across time.
5 years of environmental oxidation, stage 2 microstress fracture severity, or thermal fatigue after 1,000 cycles.
This is fascinating. So the mechanism is applying the star topology to the physics of material science. How does the architecture handle this?
Think about the real-world scenario. You are building a predictive maintenance system for aerospace engineers. An engineer inputs a high-resolution 3D scan or photograph of a brand-new, pristine aircraft turbine blade fresh off the manufacturing line. The input domain is 0 hours.
The generator's task is to translate that specific image to the target domain, 10,000 flight hours.
So the network generates a fake synthetic image of that exact turbine blade, visually simulating where it predicts the rust will form, where the microfractures will propagate, and how the heat warping will alter the geometry.
But here's where the StarGAN magic kicks in. What stops the network from just generating a picture of a generic broken piece of metal? What stops it from losing the specific identity of that exact turbine blade?
The cycle consistency loss. The network takes that hallucinated, heavily degraded 10,000-hour turbine blade, and it is forced to translate it back to the domain 0 hours.
It has to perfectly reconstruct the specific, unique molecular geometry and manufacturing microscopic imperfections of the original starting turbine.
Exactly. Because if the network just randomly slaps rust textures onto the blade or randomly hallucinates a crack, it will not know how to reverse that specific random crack to get back to the original geometry. It forces the network to learn physics-accurate, completely mathematically reversible degradation pathways.
The first experiment would involve training this temporally adapted StarGAN on vast, unaligned datasets from aviation junkyards. You have thousands of photos of new parts and thousands of photos of failed, degraded parts.
They aren't paired. You don't have a photo of the same part at year 0 and year 10. The mask vector handles the unaligned nature of the datasets, and the cycle consistency forces the network to hallucinate plausible, physics-accurate stress fractures that are mathematically bound to the original part's identity.
It becomes a literal visual time machine for structural engineering, relying entirely on the premise that physical decay is simply a transferable attribute. Just like changing hair color from brown to gray, provided you enforce incredibly strict identity preservation.
What an incredible place to wrap up our discussion. We have gone from the frustrations of perfectly pairing photos of shoes, to elegantly translating blonde hair on celebrities using spatial replication, to bridging human fMRI data, and finally reversing the flow of time on aerospace turbines using cycle consistency.
And it all stems from the architectural choices laid out in one brilliantly engineered 2017 computer science paper.
And so we leave you, our listener, with a final provocative thought to ponder off-air.
When you realize that adding a simple mask vector, just a tiny artificially appended string of zeros and ones, allows a neural network to seamlessly bridge completely unrelated datasets and discover the shared, hidden realities between them, you have to ask yourself, what other artificial boundaries in our data, or even in the strict categorizations of our scientific disciplines, are we letting hold back the next massive leap in our understanding of the world?
Are the walls between our datasets actually real, or are they just waiting for the right topology to dissolve them entirely?
Something to mull over as you look at your own data. Thank you for joining us on this deep dive into StarGAN. Until next time, keep questioning the boundaries.